So I want you to just imagine for a second that you are an energy project manager.
Okay, I'm with you.
Right. And you're standing on this pristine stretch of coastline and you're looking down at a stack of blueprints for a massive billion-dollar onshore liquefied natural gas terminal.
Oh, yeah. A total logistical nightmare.
Exactly. I mean, we are talking miles of specialized cryogenic piping, colossal concrete foundations, and this grueling construction timeline that stretches like at least 5 years into the future.
If you're lucky.
Right. And for decades, that was just the traditional heavy-duty reality of energy infrastructure. But then, you roll up those blueprints, you look out at the ocean, and just a few miles offshore, you see a single vessel.
Just one ship.
Just one ship. And that one ship is doing the exact same job as the sprawling facility you were about to build on the beach, except it arrived in a matter of months, and it didn't require a single bag of cement.
It's honestly incredible when you actually see it.
It really is. So welcome to our deep dive into the world of FSRUs. That's floating storage and regasification units. Our mission today is to explore this comprehensive guide we have on offshore energy assets and really uncover how these vessels are completely rewriting the global energy playbook.
Yeah, because it's a fundamental shift in how we think about infrastructure, We are moving away from those permanent, rigid land structures and embracing these highly mobile offshore assets.
Which just sounds so futuristic.
It does. But as we get into the mechanisms today, you're going to see that pulling this off is far more complex than just, floating a boat.
Oh, absolutely.
This is really a masterclass in marine engineering. They are manipulating extreme high energy physics in some of the most relentlessly hostile environments on Earth.
Okay, let's unpack this. Because to really understand why a company would take on the sheer challenge of engineering a floating chemical plant, we should probably start with the business problem.
Right, the economic.
Yeah, I mean, why build on the water when solid ground is right there? Is it just like to avoid buying prime coastal real estate?
Well, no, not exactly. I mean, the real issue is time. And it's also a concept that makes literally any financial planner nervous, which is sunk costs.
Oh, sure. Sunk costs are the worst.
Right. So when an energy company decides to build a traditional onshore LNG terminal, they are committing to years of preliminary work.
Before they even break ground.
Exactly. They have to secure all these complex environmental permits. They have to navigate local zoning laws and complete massive civil engineering preparations.
Just moving dirt around for months.
Exactly. They end up pouring billions of dollars into the ground before a single molecule of gas ever reaches a customer.
Wow.
That is a massive capital expenditure, or CAPEX. And once that facility is built, it is permanently locked to that specific beach for the next 40 years.
Which seems like a massive gamble, right? Because what if local power demand just drops?
Just to renewables, yeah.
Yeah. Or what if a developing market needs energy immediately and simply cannot afford to wait 5 years for, thousands of tons of concrete foundations to cure?
And that is the exact vulnerability that the FSRU solves. By chartering one of these floating units, a provider completely shifts their financial burden from CAPEX to OPEX.
Operational expenditure.
Right, OPEX. They aren't buying the equipment, they are leasing a capability. They just pay for the regasification service as they use it.
That's brilliant. So you're basically renting the factory instead of building it.
Exactly. And if the regional market changes dramatically, say 10 years down the line, the charter simply ends.
They just leave.
Yeah, the vessel pulls up its anchor and sails across the globe to serve a totally different customer.
That's why
the operator isn't left with a multi-billion-dollar stranded asset slowly rusting on their shoreline.
That flexibility makes a lot of sense. But building a hyper-advanced floating chemical plant from scratch still sounds like a massive time-consuming undertaking.
It certainly can be, which is why the downstream marine sector developed this highly strategic workaround. They don't always build FSRUs from scratch.
Oh, they don't?
No, very often they actually convert aging LNG transport carriers into FSRUs.
Wait, really? They just take an old cargo ship and slap some new machinery on the deck?
Well, it is a bit more sophisticated than that, obviously, but the premise holds. There is this existing global fleet of massive LNG carriers out there.
Right.
And as these ships age, their propulsion systems naturally become less fuel efficient for those long-haul transoceanic crossings, at least compared to the newest models.
So they're too expensive to keep sailing back and forth.
Exactly. However, their physical hulls and their highly specialized cryogenic cargo containment systems are usually still in pristine condition.
So instead of scrapping a perfectly good vessel.
Right. Engineers perform a radical retrofit.
Now, the sources mention they install regasification skids. I have to admit, I hear the word skid, and I just think of like a wooden pallet behind a grocery store. What are we actually talking about here?
Yeah, it's a bit of an understatement. A skid, in this context, is a massive modular steel framework.
Okay.
And it contains all the high pressure pumps, the heat exchangers, and the vaporizers needed to process the gas.
Oh, wow. So it's basically the entire chemical plant.
Yes. Engineers essentially build the entire plant inside this metal framework on land. They crane it onto the deck of the aging carrier, bolt it down, and integrate it with the ship's existing tanks.
That sounds so much faster.
It is. Building a new onshore plant takes about 6 years. Converting an existing carrier with these modular skids takes just 18 months.
That is an unbelievable turnaround. I mean, you can fundamentally solve a region's energy crisis in a year and a half.
Exactly.
But, looking at the sources, I noticed another term that confused me a bit. The guide mentions FSRUs, obviously, but it also talks about FSUs, floating storage units.
Right, without the R for regasification.
Yeah. It describes an FSU as just the refrigerator without the kitchen. So if an FSU only stores a liquid and can't actually process it, why would anyone lease one? Like, why choose just the fridge over the full kitchen?
Well, it comes down to the strategy of modularization. You see, an FSRU is incredibly expensive to lease because you are paying for all that high-end regasification technology integrated into the hull.
Right, you're paying for the premium model.
Exactly. But sometimes a project doesn't actually require all that technology on one single vessel. An operator might choose to lease a cheaper, simpler FSU, which just acts as a massive offshore buffer tank.
Okay.
And then they pair it with a separate dedicated barge called a floating regasification unit, or FRU.
Oh, I see. So instead of buying the all-in-one luxury model, you separate the bulk storage from the actual processing just to save money.
That is the logic, yeah. You use a standard, cost-effective vessel to hold the vast quantities of liquid, and you invest your capital into a much smaller, separate barge that sits right alongside it to handle the complex gasification.
That's really smart.
Modularity gives operators the exact balance of cost and capability they need.
Okay, so the business case. The shift from CAPEX to OPEX, the retrofits, the modular flexibility, that's all crystal clear. But I want to transition to what this machinery is actually doing out on the water.
The fun stuff.
Exactly. We keep talking about processing the cargo. What does that actually entail?
Well, the cargo we are talking about is liquefied natural gas, which is predominantly methane. And to make ocean transport financially viable, the gas is cooled to extreme cryogenic temperatures.
How extreme are we talking?
We are talking about negative 160 degrees centigrade.
That is just difficult to even comprehend.
It is deeply unnatural cold. But when methane reaches that specific temperature, it transitions into a liquid and it shrinks down to 1/600th of its original volume.
1/600th, that's insane.
It allows a single ship to carry a staggering amount of potential energy. But the challenge is that the power grids and industrial plants on the shore, they cannot utilize a supercooled liquid.
Right, they need gas.
Exactly. They need gaseous methane at ambient temperature, delivered under high pressure.
So it's essentially a massive reverse air conditioner. You're using the freezing ocean as a giant heating pad to wake up this sleeping, super dense methane.
What's fascinating here is that I understand the comparison, but let's actually take that a step further.
Okay.
An air conditioner is designed to reject heat. An FSRU is designed to aggressively absorb it. The sheer scale of thermal energy transfer required to boil that much cryogenic liquid is immense.
Because there's so much of it.
Right. And this process relies on specialized vaporizers. Engineers generally employ two main methods for this. The first is an open loop system.
Which implies it interacts directly with the environment, right? Like using the ocean water itself.
Correct. Even if the seawater feels freezing to a human compared to negative 160 degrees centigrade, the ocean is boiling hot.
Oh, that's a wild way to think about it.
Yeah. So the ship pumps massive volumes of seawater, sometimes millions of gallons a day, into the hull.
Millions of gallons.
Yeah. And this water runs through heat exchangers right alongside the LNG pipes. It transfers its natural thermal energy to the liquid methane until the methane boils back into a gas.
And then what happens to the water?
The slightly chilled seawater is then discharged right back into the ocean. It is a highly efficient design because, the primary heat source is completely free.
But surely that doesn't work everywhere. I mean, if you are stationed in the Baltic Sea in the middle of winter, the water has to be too cold to provide enough heat.
That's a major factor, yes.
Plus, I have to imagine certain coastal regulators don't want millions of gallons of artificially chilled water dumped into their local marine ecosystems.
And that is exactly the limitation of open loop systems. When you operate in colder climates or in jurisdictions with strict ecological protections regarding water discharge, you have to utilize a closed loop system.
How does that differ? If you aren't pulling heat from the ocean, where does the heat come from?
In a closed-loop setup, the vessel uses a self-contained intermediate fluid. Usually, it is a specialized mixture of water and glycol.
Oh, like the antifreeze you put in a car's radiator.
Very similar chemical principle, yes. The ship burns a small portion of fuel to heat this glycol circuit internally. The hot glycol is then pumped through the vaporizers to warm the LNG.
Oh, so it's a completely sealed off process.
Exactly, because the fluid recirculates in a closed system, it never touches the ocean, and absolutely nothing is discharged overboard. The operators maintain absolute, precise control over the temperature, regardless of the external weather conditions.
Okay, so we have this floating factory conducting massive, high-pressure thermal exchange operations. Doing that on a solid concrete foundation sounds difficult enough.
Oh, it is.
But doing it while bobbing up and down on the open sea? That just sounds like a structural nightmare.
The ocean is a notoriously unforgiving environment. When engineers build a tank on land, it remains stationary. But an FSRU is a dynamic structure constantly subjected to the kinetic energy of the sea.
Right, and unlike a transport ship that sails through storms and then finds calm waters, these units are moored in one spot permanently.
They just sit there.
Yeah, they just take the worst case wave action from the exact same angle day after day.
Which introduces severe structural fatigue. The massive regasification skids we discussed earlier are incredibly heavy.
Right.
The points where those steel frames bolt to the ship's deck experience constant, immense stress as the vessel pitches and rolls. This constant flexing is a primary reason why an FSRU has a much shorter expected operational lifespan than an onshore facility.
Really? How short?
Usually capping out at around 20 years.
Wow, just 20 years. And it isn't just the physical movement, right? I mean, we are talking about saltwater.
Oh, corrosion is huge.
Yeah. You have this massive facility covered in complex deck piping, constantly cycling extreme temperature differentials, entirely wrapped in a blanket of salty, corrosive ocean moisture. How does the ship not just rust into dust within a year?
Managing corrosion offshore is a constant battle, especially since you cannot pull an actively operating regasification plant into a dry dock for easy maintenance.
Right, because it's actively powering a city.
Exactly. So to combat this, the industry relies on highly specific metallurgy. You will frequently see the use of 5083 aluminum alloy for the vital components.
What makes 5083 aluminum so special?
It contains a specific percentage of magnesium. When exposed to harsh elements, this alloy naturally forms a highly stable microscopic oxide layer on its surface. If the metal gets scratched or dinged, that layer instantaneously reforms, sealing the raw metal away from the salt water. It effectively prevents the deep structural rust that would quickly destroy standard steel.
Okay, so that handles the ocean trying to eat the ship from the outside. But what about the cargo on the inside? I would imagine storing thousands of tons of negative 160-degree liquid presents its own set of dangers to the hull.
It absolutely does. And this brings us to a phenomenon known as cryogenic embrittlement. This is arguably the most critical engineering hazard on the vessel.
I am assuming that means the cold makes things brittle. But, how brittle are we talking?
Well, if a pipe leaks and liquid methane at negative 160 degrees centigrade spills directly onto standard carbon ship steel, the steel undergoes a rapid microscopic phase change.
Meaning?
The extreme drop in temperature causes the atomic structure of the metal to lose all of its ductility. It literally becomes as brittle as glass.
Wait, the thick steel hull of a cargo ship could shatter like a dropped drinking glass?
Yes. A sudden cold splash creates massive localized thermal contraction. The steel shrinks so violently and becomes so brittle that it can crack and tear apart under its own structural tension.
Here's where it gets really interesting. How do engineers possibly secure the integrity of a vessel when a single spilled cup of cargo could crack the hull?
Through intense secondary containment and thermal isolation, the cargo is typically held in what are called Type B independent tanks.
Okay.
These are massive spherical or prismatic structures sitting inside the hull, and they are distinct because they feature specialized drip trays beneath them.
Oh, I see. So if a hairline fracture develops in the primary tank, the cryogenic liquid falls into the designated tray rather than directly onto the floor of the ship.
Precisely. The goal is to catch any leak before it ever touches the load-bearing outer hull, but the protections extend outside the tanks too. During ship-to-ship transfers, you will often see FSRUs deploying water curtains. The vessel actively pumps continuous cascades of ocean water down the exterior side of its own hull.
I was going to ask about that. I saw pictures in the guide. Why are they watering the side of the ship? Does it just wash the spilled methane away?
It is not about washing it away, it is about heat transfer. The cascading water acts as a thermal buffer.
Ooh.
Yeah, if a transfer hose ruptures and sprays cryogenic liquid against the side of the ship, the extreme cold hits the flowing, relatively warm seawater first.
So it never touches the bare metal.
Right. The thermal energy of the water rapidly transfers to the methane, forcing it to boil off into a vapor before it can freeze the steel hull into a shattered state. You have to remember, the crew isn't just managing a flammable substance, they are constantly managing a thermal bomb.
Managing a thermal bomb, fighting saltwater corrosion, and running massive heat exchangers. It sounds like an operation that would require astronomical amounts of power.
It really does.
Which brings up an interesting contradiction. We hear a lot about how stringent the maritime industry is becoming regarding pollution.
Yes, very strict.
So how do you power a colossal floating chemical plant without creating a massive cloud of emissions right off the coast of a city?
That is a crucial point. The international maritime regulatory landscape is governed by a treaty known as MARPOL Annex 6. It lays out incredibly strict global limits on the amount of sulfur oxides and nitrogen oxides that ships are allowed to emit.
And I imagine the rules are even tighter if the FSRU is parked right near a populated coastline.
They are. In designated emission control areas, or ECAs, places like the North Sea or along the North American coastline, the allowable limit for sulfur emissions drops drastically, down to just 0.1%.
Wow, that's practically nothing.
Right. And standard heavy fuel oil, which powered ships for decades, simply cannot meet that standard.
So what is the alternative? Do they have to string a giant extension cord from the beach to run the pumps?
The elegance of the FSRU is that the solution is already on board. Liquefied natural gas inherently solves the sulfur problem because all of the natural sulfur is stripped out of the gas during the liquefaction process long before it is ever pumped onto a ship.
Well, that makes sense.
But the real engineering brilliance is how the vessel utilizes boil-off gas.
Boil-off gas, like steam coming off a pot of boiling water.
Essentially, yes. Even with state-of-the-art insulation, a small amount of environmental heat inevitably bleeds into the cryogenic tanks over time.
You can't keep it perfectly cold forever.
Exactly. This causes a fraction of the liquid cargo to naturally evaporate or boil off back into methane gas. In older generations of transport ships, this rising vapor pressure was a major problem.
Because it would build up inside the tank.
Right. To prevent the tanks from overpressurizing and bursting, crews